Floyd Ogilvy. You've seen me in such fine quality, epic chemistry educational videos as chemical balance. Is it possible amongst those who make decisions for the rest of us? And why is chemistry like a balancing act? Okay, in this video we're going to be looking at balancing equations. And we have to look at what chemical equations are, and we go from there. So for chemical equations, it's describing what's happening. We have our reactants, you can think of those as ingredients, and then products, which is our end result. Sometimes we're interested in the actual solid physical product. Other times we may not be interested in that. We may be interested in the heat energy that is being given off. You know, like a hand warmer, for example. But if we think about it, chemical equations, in a way, are like sentences that tell us what's going on. We start out with reactants, we end up with products. Now, the equations should be balanced. That is a key thing. Just because the number of atoms of reactants should equal the number of atoms of products. That is clear because the law of conservation of matter, the law of conservation of mass, that needs to be obeyed. I only know of one individual who totally violated it in a rather spectacular ways. I don't know, feeding thousands of people with bread and fish, you know, when they started out with 5 loaves and 2 fish, you know, changing water into wine. Those are clearly, obviously violations of the natural laws of nature. But you know, the one who made it, he gets to break it. It works that way. So when we look at this here we're going to burn some methane and oxygen. We get carbon dioxide and water. We can look at reactants and products, and we can break it down to C, H, and O. One on each side here. Okay, then we have 4 hydrogens here. We have 2 hydrogens over here, 2 oxygens on this side, and 1, 2, 3 oxygens on this side. So this is a way to do this, okay, for arranging it. Now, when we look at it, we need to take care of balancing. We really didn't need to worry about the carbons, okay, because they're balanced. Now, in this case here, we chose to balance the hydrogens. Does it make a difference which one you start to balance first? No, not really. Personally, I wait toward balancing the hydrogens at the end of things. Or in this case, you can wait till the oxygen at the end of things, simply because oxygen is O2 by itself. So we can really mess around with the numbers later. So in this case here, we want to make the number of hydrogens equal to each other, so we put a 2 in front of here. We never mess with these numbers, these subscript numbers. We only mess around with the coefficients. Okay, that's a very key thing for us. So we got 2 here, so that gives us 4 hydrogens. It also gives us 2 oxygens here, which we see in our next slide, supposedly. Okay. So you can see in our next slide here, now we have 4 hydrogens. We also now have 2 and 2 times 1, 2 for 4 oxygens as well. So we're looking pretty good here. We still have our 1 carbon. We still have 4 hydrogens. We're good to go there. And here we have 4 oxygens on this side, but 2 on this side. How do we solve that? Well, easily we can just go ahead and put in a 2 in front of the O2. So now what we have here for our reactants, we still have our 1 carbon on each side. Okay, we have our 4 hydrogens on each side. And then, last but not least, we have our 4 oxygens on each side. This works. This will work perfectly well. And thus, this is, in fact, balanced. This is what we mean when we're saying we have a balanced equation. That the number of each type of atom is the same on both sides of the equation arrow. Our reaction arrow, if you will. Okay, that's a very important thing, that balancing. Otherwise, there's going to be some issues. All right. Now, there are abbreviations that we do have in terms of chemical reactions. So here, when we see the S in parentheses with the arrow going down, that means a solid is being formed. In other words, it is what we call the
precipitate. Now, the precipitate, some people might think in terms of precipitation. Raindrops keep falling on my head. Precipitation could be snow, it could be rain, it could be a combination of snow and rain together, hail, okay, which is great if we talk about apes, if we talk about the weather and earth science, things like that, what we don't get enough of here in Southern California. But if you have some equations where you end up having a reaction where some solid is being formed in a solution, you have this precipitate that forms and drops to the bottom. That's what this covers. And again, if you're not part of the solution, you're the precipitate. Okay. Here we got gas. Gases will be generated. Gases can be used in a chemical equation. So we're good for that. Now AQ means aqueous. Now aqueous, it basically means full of water. This refers to a specific solution of something. Okay? If we were to melt iron from a metal into a liquid, okay, hot, 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 we can sit there and say, oh, that's liquid. That's liquid iron. It's not aqueous because it's not mixed with water. Now, if we talk about mixing salt with water, we have a salt solution, we can say that's aqueous. That would be a very important thing. Okay? Heat. Well, let's face it, some of the reactions we are going to be adding heat. It could be the Bunsen burner, okay, that's one thing, but it could also be a hot plate, okay? The heat is on, the heat is on. Okay, moving on. The triangle here is a nice way of saying the heat, okay? And you'd say, but that's the delta sign in math. Yes, it's also the delta sign that's used in the sciences that represents change. Okay, like delta H, delta T, delta G, delta S. You will get into that later on. Okay, but this means also heat. Okay, so we don't necessarily use the word heat. We can use this to tell us that it's heat. And then here, well, there's the catalyst. Now, the idea behind a catalyst, it's something that you add to the reaction to lower the needed amount of activation energy to make the reaction happen more easily. And usually we want a reaction to go faster. In AP Biology, we refer to those as enzymes. Right. Oh my gosh, you made a connection between AP Biology and AP Chemistry. That's right, Odell, I did. Okay? Because we don't have that connection with that in AP Calculus, I'm just saying. And of course, here's our plain old straight arrow here. Okay, so this is our basic punctuations that are there. So if we were to go and do some practicing on here, I am going to leave you guys with a worksheet that you can go ahead and work on practicing. You guys can work together in groups on this, okay, since it is for this particular assignment. All right, but I'm going to go ahead and I'm going to work through one of these with you. Let me check over here. Ah, yes. So let's take a look here. Cr plus S8. Oh, hey, look, that was the previous period. What do you know? All right. Cr and S8. Ooh, wow, that's Cr S8 plus, and what else do we have? Oh, Cr plus S8. Oh, I'm paying attention. Okay. Cr plus S8 gets us Cr2S3. Cr2S3. This almost sounds like a droid for the new upcoming Star Wars movie. Seriously. R2 has a special place in my heart. Okay. Not that I'm sitting there saying that episodes 4 and 5 were the best. Okay. Alright, so let's look at this. Let's break it down. So we have two players. We have Cr. Okay, we have Cr and we have our S. Okay, now, so over here we have 8 for our sulfur. And here we have 1 for the chromium. Over here we have 2 for the chromium and 3 for the sulfur. Okay, which one would I want to start balancing first? Because I picked a relatively small one here. I would go and balance out the sulfurs. Let me tell you why. The CR would be very easy. We can just simply put a 2 in front of it and be done. I would wait until the end for this one, because we can put any old number here. Now remember, we cannot add it here because that's the coefficient. We can't do it that way. We cannot change these numbers. So that means we have to change these coefficients, not the subscripts. So I'm looking here. I have 8 sulfur on this side, 3 on this side. Now what number does 8 and 3 go into evenly? Now if it doesn't come to you immediately, what you can do is multiply the numbers together and you'd find the number that they have in common. 8 times 3 is 24. Okay, so that would mean I would have to put in a 3 in front of here. And then 3 times 8, that gives me 24. Now over here, I've got a 3. That means I need to put an 8 in here. So 8 times 3 is 24. So now my sulfurs are balanced out. My chromium is not. But when you look at it, how many chromium do I now have on this side? Because I have to cross this, and now it's 16. Because 2 times 8 is 16. So this is what we have. Our sulfurs are good. We don't have to mess around with them anymore. So let's look at the chromium here. Okay, I need 16. Sheesh, I would put 16 here. I've got 16 chromiums on each side, 24 sulfurs on each side. Dun, 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 dun. Okay, we solved it. Okay. Any questions? I'm on video! But at any time, remember, you can put this back. You can go ahead and redo the video at any time. Okay, let's take a look at this one here for a moment. Okay. I want to point out something about this equation here. And that is when you split it up, you see that PO4? You can put that together as one unit. So you can have the PO4 on, when you're working your products and your reactants, you can have the PO4 like this. And the reason is it doesn't change. So you start out with 1 on the reactant side, 2 on the product side. So that's what you've got right here. Okay? Now, let's see, what else? Okay, let's take a look at this problem here. This is going to be, again, this is more practice. Now, when you look at a word equation like this, when you look at a word equation like this here, okay, you have to figure out what is solid iron 3 sulfide. So when we look at iron 3 sulfide, there's a couple of things you need to notice. You have an iron. So here is an Fe, and what kind of a charge does it have? It's a 3+ charge because of that Roman numeral. That's the clue that it tells me this. Okay? And then there's sulfide. Well, wait a minute. What's the sulfide ion? And you see, that was why I had you guys do those prefixes and suffixes during the summer as part of the summer work, like chloride, sulfide, sulfate, sulfite, those, because that would come very handy for this. The sulfide is simply a sulfur with a -2 charge to it. So you can't say FeS because the charges are not going to balance each other out. When you see this, it is reasonable to assume that the charges are not balancing each other out. I'm going to rephrase that. When you see a problem like this, iron 3 sulfide, that means the charge is balanced out. It's not an ion, it's not a cation, and it's not an anion. So that means it's a 0 charge. So we have to balance these two within each other. Well, to make the long story short, it'll be Fe2S3. That's what it would look like when it's balanced out, okay? Now it says here it's a solid, so it's reasonable to say, okay, it's going to look like that. It reacts with gaseous hydrogen chloride. Okay, hydrogen chloride, well, you should know what hydrogen chloride is, and then to form solid iron 3 chloride and hydrogen sulfide gas. Okay, so they would want you to go balance these out, put them in the equation, and then balance the equation out for that. Okay, so what would that look like? Well, you'd have an Fe2S3, that's a solid, plus it's a gaseous hydrogen chloride. Well, what do I know about the chloride ion? Well, it's in that halogen category, and they all typically have a -1, so that's going to be an HCl, and that's in the form of a gas. Okay, so that's what I'm going to get. Now we have solid iron, and it says to form. Okay, when we look at this word here, to form, that tells us this is what it's going to result in. We got the reactants taken care of, now we're going to be looking at the product. So when we're saying to form, that should be a message of, uh-oh, this is the product, this is what we're going to get. So we have solid iron 3 chloride. Well, again, what's iron 3? Iron +3 charge. The chlorine, or the chloride, has a -1 charge, so it's going to be FeCl3, and that's a solid, right? Plus hydrogen sulfide gas. That would be 1 hydrogen and a sulfur, but the sulfur has a -2 charge to it. So you're going to have to do this. So this is what you guys have here. So we went from iron 3 sulfide to iron 3 chloride, and this is dihydrogen sulfide or hydrogen sulfide gas. Okay, sticky. This is the main component of the gas that we all give off. Okay, that's what causes the smell. It just does. So now you can go ahead, given this information, now you can go ahead and try to balance it. Okay, let me check my other thing here. It's not doing that. Okay. Try that. Okay. So, let's go through. Let's deal with meaning. So, a balanced reaction can be used to describe a reaction in molecules and atoms. It's not telling us about the grams, okay? Because the chemical reactions, naturally, they're going to happen molecules at a time, or dozens of molecules at a time, or moles of molecules at a time, okay? And that's where the stoichiometry comes in. Given an amount of either starting material or product, tell us what the other quantities are, and we can use the conversion factors from molar mass, like grams to moles, and moles to moles, those kinds of things. Okay? So, we're going to stop here for this video, and you're going to be working on your worksheets for that. And I would expect that you guys could turn that in. Let's see, today is Tuesday. Okay, you should be able to turn it in Wednesday, along with your density lab report, 1 per group. Okay? All right, guys. At this point, I am now signing off. I won't do anything funny. I won't do anything funny at all. No, nothing funny at all. Not in the least. Nope. Nope, 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 not at all. Not at all. Not at all. Bye.